Article 392 addresses cable trays. While a specific product may not be classified as a cable tray, if it serves a similar purpose by supporting and protecting cables, it is reasonable to infer that Article 392 applies. Article 300.8 discusses mixing mechanical systems. This article explicitly prohibits mixing electrical cables with mechanical systems, for example, air and hydraulic piping, unless specifically permitted by the Code. The argument that Article 300.8 does not apply because cable protectors are not explicitly mentioned is invalid. The general prohibition applies to all mechanical systems, regardless of their specific name. The National Electrical Code is designed to protect life and property from electrical hazards. Mixing electrical cables with mechanical systems can create potential safety risks such as electrical interference or damage to mechanical systems, physical damage to cables by mechanical systems, or inadvertent energization of mechanical systems. A reference Canadian ruling does not have authority in the United States. The National Electrical Code and local electrical codes must be followed for installations in the United States. It is considered a best practice to keep electrical cables separate from mechanical systems to minimize potential hazards and ensure the safe operation of both systems. Therefore, based on these arguments and considerations, it may not be permissible to install Class 1-2 of 3 electrical circuits alongside air and hydraulic piping using a specific cable protector product in the United States. Let's delve deeper into these code-based arguments. Examining Article 392 more closely, we can understand the intent behind regulating cable trays. Cable trays provide a structured support system for cables, ensuring they are properly managed and protected from physical damage. The Code specifies requirements for cable tray construction, installation, and grounding to maintain electrical safety. Even if a product is marketed as a cable protector and not a cable tray, it's essential to evaluate whether it performs the same function. If it does, applying Article 392 is justified. Article 300.8 is very explicit about the separation of electrical and mechanical systems. This separation is crucial for several reasons. Firstly, it prevents electrical interference. Electrical cables can emit electromagnetic fields that can interfere with the operation of sensitive electronic equipment used in mechanical systems. Secondly, physical damage is a major concern. Mechanical systems, especially those involving moving parts or fluids under pressure, can potentially damage electrical cables if they are in close proximity. A leak in a hydraulic system, for instance, could saturate the insulation of electrical cables, leading to short circuits or ground faults. Thirdly, inadvertent energization of mechanical systems poses a significant safety risk. If an electrical cable comes into contact with a conductive part of a mechanical system, that part could become energized, creating a shock hazard for anyone who touches it. The National Electrical Code's scope is to safeguard people and property from hazards arising from the use of electricity. This includes minimizing the risks associated with electrical shock, fire, and explosions. The Code achieves this by establishing minimum safety standards for electrical installations. These standards cover everything from wiring methods and overcurrent protection to grounding and bonding. When assessing a proposed installation, it's crucial to consider the potential hazards and whether the proposed methods adequately mitigate those risks. A ruling from a Canadian authority does not supersede the requirements of the National Electrical Code in the United States. Electrical installations in the United States must comply with the National Electrical Code and any applicable local electrical codes. Local codes may be more stringent than the National Electrical Code, but they cannot be less stringent. It's always advisable to consult with local electrical inspectors to ensure compliance with all applicable codes and regulations. Best practices dictate that electrical and mechanical systems should be physically separated whenever possible. This separation can be achieved through various means, such as using separate raceways for electrical cables, installing barriers between electrical and mechanical systems, and maintaining adequate spacing between systems. Proper labeling and identification of electrical and mechanical systems are also essential for safe operation and maintenance. To further illustrate the importance of these code requirements, let's consider a few practical examples. Imagine a scenario where electrical cables are routed alongside air conditioning ducts. Condensation from the ducts could drip onto the cables, causing corrosion and potentially leading to electrical faults. Or consider a situation where electrical cables are run near hydraulic lines. A rupture in a hydraulic line could spray hydraulic fluid onto the cables, damaging the insulation and creating a fire hazard. In both of these scenarios, the close proximity of electrical and mechanical systems increases the risk of electrical hazards. These risks can be mitigated by adhering to the code requirements for separation and protection. To summarize, the National Electrical Code prohibits the mixing of electrical and mechanical systems unless specifically permitted. This prohibition is intended to protect people and property from electrical hazards. While a specific product may be marketed as a cable protector, it must still comply with the applicable code requirements. It is always best practice to keep electrical and mechanical systems separate to minimize potential hazards. If you have any questions about the code requirements for electrical installations, consult with a qualified electrical inspector or engineer. They can provide guidance on how to ensure compliance with all applicable codes and regulations. Remember that electrical safety is paramount, and it's always better to err on the side of caution when it comes to electrical installations. By following the code and best practices, you can help to prevent electrical hazards and ensure the safe operation of electrical systems. Let's consider some additional points. Firstly, the specific class of electrical circuits being installed, class 1, 2, or 3, doesn't fundamentally change the prohibition against mixing electrical and mechanical systems. The primary concern remains the potential for electrical hazards, regardless of the voltage or current levels involved. Secondly, the type of mechanical system, whether it's air or hydraulic piping, also doesn't alter the basic principle of separation. Both air and hydraulic systems can pose risks to electrical cables, either through physical damage, fluid leaks, or temperature fluctuations. Thirdly, the physical construction of the cable protector itself is relevant. If the cable protector provides adequate physical separation and protection for the electrical cables, it may be considered a safer alternative to simply running the cables alongside the mechanical systems without any protection. However, the cable protector must still meet all applicable code requirements for electrical enclosures and raceways. Fourthly, the presence of a Canadian ruling allowing a particular installation doesn't automatically make it acceptable in the United States. The National Electrical Code is the governing standard for electrical installations in the United States, and it must be followed. A Canadian ruling may be based on different codes or standards, or it may be specific to a particular set of circumstances. Fifthly, the argument that the cable protector is not a cable tray and therefore exempt from Article 392 is not necessarily valid. The code is often interpreted based on the intent and function of a product, not just its specific name or classification. If the cable protector performs the same function as a cable tray, it may be subject to the requirements of Article 392. Sixthly, it's important to consider the long-term implications of an installation. Even if an installation appears to be safe at the time of installation, it's possible that it could become unsafe over time due to factors such as wear and tear, environmental conditions, or changes in the operation of the mechanical systems. Therefore, it's crucial to design and install electrical systems in a way that minimizes the potential for future problems. Seventhly, communication and coordination between different trades are essential for ensuring electrical safety. Electrical contractors, mechanical contractors, and other tradespeople should work together to ensure that electrical and mechanical systems are properly installed and maintained. Eighthly, ongoing maintenance and inspection of electrical systems are crucial for identifying and addressing potential hazards. Regular inspections can help to detect problems such as damaged cables, loose connections, and corrosion. Ninthly, it's important to stay up to date on the latest code changes and industry best practices. The National Electrical Code is updated every 3 years, and it's essential to be aware of any changes that could affect electrical installations. Tenthly, when in doubt, it's always best to consult with a qualified electrical engineer or inspector. They can provide expert guidance on how to ensure compliance with all applicable codes and regulations. Now, let's elaborate on the potential safety risks associated with mixing electrical and mechanical systems. Firstly, electrical interference can disrupt the operation of sensitive electronic equipment used in mechanical systems. This interference can manifest as errors in data transmission, malfunctions of control systems, or even complete system failures. Secondly, physical damage to cables can occur due to contact with moving parts, vibration, or exposure to extreme temperatures. Damaged cables can lead to short circuits, ground faults, and other electrical hazards. Thirdly, fluid leaks from hydraulic or pneumatic systems can saturate the insulation of electrical cables, reducing their dielectric strength and increasing the risk of electrical breakdown. Fourthly, inadvertent energization of mechanical systems can create a shock hazard for anyone who comes into contact with the system. This can occur if an electrical cable comes into contact with a conductive part of the mechanical system, or if a ground fault develops in the electrical system. Fifthly, fire hazards can arise from overheating of electrical cables due to overloading or short circuits. Electrical fires can spread quickly and cause significant damage to property and equipment. Sixthly, explosion hazards can occur in areas where flammable gases or vapors are present. Electrical sparks or arcs can ignite these gases or vapors, leading to an explosion. Seventhly, corrosion of electrical components can occur due to exposure to moisture, chemicals, or other corrosive substances. Corroded components can fail prematurely, leading to electrical hazards. Eighthly, improper grounding of electrical systems can create a shock hazard for anyone who comes into contact with the system. Grounding is essential for providing a safe path for fault current to flow back to the source, tripping the overcurrent protective device and de-energizing the circuit. Ninthly, lack of proper overcurrent protection can allow excessive current to flow through electrical cables, leading to overheating and fire hazards. Overcurrent protective devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a safe level. Tenthly, improper installation of electrical equipment can create a variety of hazards, including loose connections, exposed conductors, and inadequate clearances. Proper installation is essential for ensuring the safe and reliable operation of electrical systems. To further clarify the application of Article 300.8, let's consider some specific examples of mechanical systems. These include, but are not limited to, heating, ventilation, and air conditioning, also known as HVAC systems, plumbing systems, hydraulic systems, pneumatic systems, steam systems, and process piping systems. All of these systems involve the movement of fluids or gases, and they all have the potential to damage electrical cables if they are in close proximity. The code requires that electrical cables be separated from these systems by a sufficient distance, or that they be protected by a suitable barrier. The purpose of this separation is to prevent electrical hazards and to ensure the safe operation of both the electrical and mechanical systems. It's also important to note that the code applies to all types of electrical cables, including power cables, control cables, and communication cables. The potential hazards are the same, regardless of the type of cable. Therefore, it's essential to follow the code requirements for all electrical installations. Finally, let's emphasize the importance of using qualified electrical contractors and engineers. Electrical work is inherently dangerous, and it should only be performed by individuals who have the necessary training and experience. Qualified electrical contractors and engineers are familiar with the code requirements and best practices for electrical installations, and they can help to ensure that electrical systems are installed safely and reliably. When hiring an electrical contractor or engineer, be sure to check their credentials and references. Ask about their experience with similar projects, and make sure they are properly licensed and insured. By using qualified professionals, you can help to minimize the risk of electrical hazards and ensure the safety of your property and occupants. To reiterate, electrical safety is a critical aspect of any building or facility. Mixing electrical and mechanical systems can create potential hazards that can lead to serious consequences. By understanding and following the code requirements and best practices, you can help to prevent these hazards and ensure the safety of your property and occupants. Always consult with qualified electrical professionals for any electrical work to ensure compliance and safety. Let's now delve into specific scenarios and how the code addresses them. Firstly, consider running low-voltage Class 2 circuits alongside HVAC ductwork. Even though Class 2 circuits are limited in power, the risk of physical damage to the wiring from condensation or vibration from the ductwork still exists. Article 300.8 would still apply, requiring separation or suitable protection. Secondly, imagine a situation where hydraulic lines are installed above a suspended ceiling and electrical cables for lighting fixtures are also run in the same space. A leak in the hydraulic line could drip onto the cables, potentially causing damage. The code would require that the hydraulic lines be properly supported and that the electrical cables be protected from the potential for fluid exposure. Thirdly, let's say that pneumatic lines are used to control automated equipment in a factory setting. Electrical cables for the control system are run alongside the pneumatic lines. The code would require that the electrical cables be separated from the pneumatic lines to prevent physical damage or interference. Fourthly, suppose steam pipes are used for heating in a building. Electrical cables are run in close proximity to the steam pipes. The code would require that the electrical cables be insulated and protected from the heat generated by the steam pipes. Fifthly, if process piping is used to transport chemicals in a manufacturing facility, and electrical cables are run alongside the process piping, the code would require that the electrical cables be resistant to the chemicals being transported in the process piping. In all of these scenarios, the key is to assess the potential risks and to take appropriate measures to mitigate those risks. The code provides guidance on how to do this, but it's always best to consult with a qualified electrical professional to ensure that the installation is safe and compliant. Furthermore, the type of raceway used for electrical cables can also affect the level of protection provided. For example, rigid metal conduit provides a higher level of physical protection, while flexible metal conduit provides a lower level of protection. The choice of raceway should be based on the specific application and the potential risks involved. In addition to physical protection, it's also important to consider the grounding and bonding requirements for electrical systems. Grounding and bonding are essential for providing a safe path for fault current to flow back to the source, tripping the overcurrent protective device and energizing the circuit. Improper grounding and bonding can create a shock hazard for anyone who comes into contact with the system. The code provides detailed requirements for grounding and bonding, and it's essential to follow these requirements carefully. Finally, let's emphasize the importance of documentation. It's essential to document all electrical installations, including the location of cables, raceways, and equipment. This documentation can be invaluable for troubleshooting problems and for making future modifications to the electrical system. Documentation should include detailed drawings, specifications, and test results. The drawings should show the location of all electrical components, and the specification should list the materials used and the installation methods followed. The test results should verify that the electrical system is operating properly and that it meets all applicable code requirements. By documenting all electrical installations, you can help to ensure the long-term safety and reliability of the electrical system. In conclusion, mixing electrical and mechanical systems can create potential hazards that can lead to serious consequences. By understanding and following the code requirements and best practices, you can help to prevent these hazards and ensure the safety of your property and occupants. Always consult with qualified electrical professionals for any electrical work to ensure compliance and safety. It's also worth noting that some manufacturers offer integrated systems that combine electrical and mechanical components into a single unit. These systems are typically designed to meet specific safety standards, and they may be acceptable under the code. However, it's important to carefully review the manufacturer's documentation to ensure that the system is installed and operated in accordance with the code requirements. Furthermore, some jurisdictions may have specific requirements for integrated systems, so it's essential to check with the local authorities before installing such a system. In addition to the code requirements, there are also a number of industry best practices that can help to improve electrical safety. These best practices include using high-quality materials, following proper installation procedures, and performing regular inspections and maintenance. High-quality materials are more durable and reliable, and they are less likely to fail over time. Proper installation procedures ensure that electrical components are installed correctly and that they are properly protected from damage. Regular inspections and maintenance can help to identify potential problems before they become serious hazards. Finally, it's important to remember that electrical safety is everyone's responsibility. Everyone who works with or around electrical systems should be aware of the potential hazards and should take steps to protect themselves and others from those hazards. This includes following safety procedures, wearing appropriate personal protective equipment, and reporting any unsafe conditions to the appropriate authorities. By working together, we can create a safer environment for everyone.